today we're going to prove the mean value theorem, which says if you have a function f and it's continuous on the closed interval AB and it's differentiable on the open interval AB, then there is a C in AB such that the derivative of C is equal to f for b minus f for a over b minus a. What is going on here? So we need to look at this before we're going to be able to prove it. We have to understand what we want to prove. So we have this function that goes from a to b. Suppose that's f of a. No, I just want to raise that a little bit higher. I think that might be helpful in the end. Okay, so here is f of a, and say higher up is f of b, and here is the curve f of x. Now, this line, the slope of that line, slope of the secant line is, well, it's the change in y, which is f of b minus f of a, divided by the change in x. X is b, and over here x is a, over b minus a. And you go, whoa, that's this part here. So we have the slope of this happens to be a slope, and it equals to a number, this number. And they're saying that there is a c where the slope of the tangent line at C has the same value of this. Well, yeah, right here. Right here, the slope of the tangent line, right at that C, f prime of C is say equal to k, where maybe I call that k. So now, if we look at Rolle's theorem says that here's f of a and f of b has to be the same height, and there is some other function. And now let's just look at this. The slope of that line is f of b minus f of a over b minus a. Fair enough, it equals 0. But it's still f of b minus f of a, etc. So there's a c that actually equals this. You know, this is pretty much what we're saying about Rolle's theorem. The only difference is f of a and f of b don't have to be equal to one another. I wish I had the ability to do what I'm about to say, but if I took this figure right here and rotated it like that, I get this figure right here. I get that. There's no difference. So it would be good if I could, so let me just erase down here. It'd be good if I could somehow find another function where, call it h of x, where h of a is 0 and h of b is 0. And I look and I think, and then I say, you know what? Let's look at this height. Let's call that height h of x. And then I'm like, well, you know what? As I get closer and closer to 0, in fact, at 0, at x equal a, h of a is 0. And as I look at the heights as they get closer and closer to x equal b, the height's going to be 0. That is, however we define h of x, h of a will equal 0 and h of b will equal 0. Sounds like rolls down. Okay, so now we need to know what this distance is. Well, basically, it's going to be this height minus this height. Well, I know this height up here. So for this given x, this height up here is f of x. Now, what is that height? Well, that's the y value of the line. We need to find the equation of this line. Okay, so that shouldn't be bad. We know that y minus, so let me be crystal clear. We have the slope of the line and we have a point on the line. We can take AF of A, that is this point here, or we could have picked that point. So we know that the equation of the line is y minus the y value equals to, well, m times x minus the x value. Well, m is f of b minus f of a over b minus a, m times x minus the x value. That's the equation of that line. Well, let's write this down more neatly. Y minus, so let me write it down again, and then we'll clean it up. Over b minus a times x minus a. And all I'm going to do is bring that to the other side. So the equation of the line is m, well, f for b minus f for a over b minus a, all of this times x minus a, just like it was. But now I bring this over. Since it's minus, it comes over as plus f of a. So now we have the equation of the line, which I will call y. Okay. So now, what is h of x? H of x is in here. This is h of x. It's, remember, if this is x, straight across is f of x. And straight across is y. Well, sorry. Straight across from that point is y. So h of x is f of y minus y. H of x is f of x minus y. Okay, so h of x is f of x minus y. So I need to take away this piece, f of b minus f of a over b minus a, all of this times x minus a, and I have to take away that part of y, minus, what's going on, minus f of a. Now, let's make sure that what I'm claiming is true. I claim that h of a is going to be 0. Well, it's f of a minus f of b minus f of a over b minus a times x is a times a minus a, which is 0, minus f of a. Since this is 0, when you multiply it by that, that's 0. And look at this. F of A minus F of A really is 0. Now, what's H of B? What is H of the letter B? So I plug in B wherever there's an X. So I get F of B minus the slope stuff, F of B minus F of A over B minus A times B minus A, because X is B, minus F of A. Well, first I will notice that this cancels out. So let's be very careful and let's see what we get. We get F of B minus F of B minus F of B, and we have to take away a negative F of A. That becomes plus F of A, and then we have to take away F of A. Well, yeah, that's 0. F of B minus F of B is 0, plus F of A minus F of A is 0. It's 0. Okay, so that was just to verify it, but of course it had to work, so you didn't have to check. And the reason it had to work was because of the way we defined it. We defined it to be the distance between these two curves. And at B is going to be 0. At A is going to be 0 by definition. Okay, so now let's see. I guess we should say this. F of X is given to be continuous on the interval AB. This here is a line which is continuous everywhere, in particularly on AB, closed AB. And this is a constant. It also is a line. Y equals 7. It's a line, and it is constant on, is continuous on everywhere, and particularly on the closed interval AB. All right. Now, let's talk about differentiability. So, therefore, H is continuous. H being the sum, well, only well, yeah, we're adding this. Since H is the sum and difference of continuous functions, it will be continuous. Okay. So let's write that down. F of X is continuous on AB. Reason given. F of B minus F of A over B minus A, a number, times X minus A. This is continuous on AB. Why? It's a line. F of A. F of A. Oops, that's not an A. F of A is continuous on AB. Why? It's a line. Therefore, H of X is continuous on AB. Why? Closed AB. Why? Sum and differences of continuous functions are continuous. Okay, so we have H is continuous. Now, same argument. F of X is differentiable on AB. Why? Given. That mess here, let's see, this mess here, the line. F for B minus F for A over B minus A times X minus A. Now, only a line that says X equals a constant doesn't have a derivative. It's a vertical line. This is not a vertical line. This line has a slope. Maybe the slope is 0, but then their function is still differentiable. The derivative will not be 0. Oops. This is differentiable on AB because it's a line and it's not vertical. The only line that doesn't have a derivative, that is, doesn't have a slope, is a vertical line. Okay, now F for A is differentiable on AB. Why? Because the derivative is 0. That is, if I know what the derivative is, then it must be differentiable. I can tell you what the derivative is. The derivative of F for A is 0. Okay, so h of x is differentiable on AB. Why? The sum and the differences of differentiable functions is differentiable. Okay? So now, although you needed to write all this, I need to erase it because I need the space. So h of x satisfies all the conditions for Rolle's theorem. That's important. Why? Because why does it satisfy? Because h of A equals h of B. They both happen to equal 0, but h of A equals h of B, and h is continuous on the closed interval AB, and h is differentiable on the open interval AB. So, there must exist a C in the open interval AB such that h prime of C is 0. Okay. So, before we can compute h prime of C, let's figure out what h prime of x is. H prime of x is, well, it's the derivative of f of x, which is f prime of x, minus the derivative of a constant times x minus a. So that derivative is going to be the constant times the derivative of x minus a, which is 1. And I won't bother multiplying that by 1. Minus the derivative of a constant, which is 0, and I won't bother writing this. Okay, now we know by Rolle's theorem that h of x, h prime of c, which is also known as f prime of c minus f for b minus f for a over b minus a, equals 0. Well, wait a minute. If you subtract these two, which we're doing, and you're getting 0, it must be that those two are equal to one another. Okay, the instant you subtract two things and you get 0, you can immediately say, oh, those two things in the yellow boxes have to be equal. They have no difference. Okay, so we show that there exists a C and a B such that f prime or C is equal to that slope of the secant line from A to B. And this is exactly what we wanted to show. So basically, all we did was rewrite f of x as another function. We used f of x to come up with a function h of x that satisfied Rolle's theorem. And as a consequence, so we definitely knew that there was going to be a C and a B such that h prime of C was 0 because it satisfied Rolle's theorem, but that meant that this minus that, which was h prime of C, equals 0. That is, we got the conclusion we wanted. That completes this video with one exception. So I now want to say the following. Now that Rolle's theorem is just a special case of the mean value theorem. Okay, please come back, watch some more videos.